5 petabytes of data cannot travel through the internet. The Event Horizon Telescope team had to physically ship hundreds of hard drives across the Atlantic Ocean. But your own brain processes more data in 1 second than that entire cosmic observation. In April 2017, 8 global radio observatories pointed their dishes at galaxy Messier 87, 55 million light-years away. They were attempting the impossible, to photograph the shadow of a 6.5 billion sun black hole. The problem was not simply distance. The problem was the nature of seeing itself. To resolve an object as small as a black hole's event horizon from Earth, you need a telescope the size of our planet. No single dish could ever achieve that resolution. The solution was a technique called Very Long Baseline Interferometry, or VELBI, a method that effectively stitches together signals from observatories scattered across the globe, synchronizing them with atomic clocks so precisely that the Earth itself becomes a single enormous lens. But this trick comes at a cost. The data it produces is monstrous. Each observatory recorded its observations onto hard drives, generating a total of 5 petabytes, 5 million gigabytes, of raw radio signals. There was no cable on Earth that could handle that transfer. So the drives were packed into crates and flown to 2 processing centers, Haystack Observatory in Massachusetts and the Max Planck Institute for Radio Astronomy in Germany. When the data arrived, the real battle began. The correlation process, which aligns the signals from each telescope with sub-millisecond accuracy, took weeks of supercomputer time. But correlation was only the first step. What emerged from that process was not an image. It was a scattered, incomplete set of measurements, a sparse collection of data points that looked nothing like a photograph. The array had captured only a fraction of the information a single, full-sized telescope would gather. The team faced a brutal mathematical problem. How do you reconstruct a picture from almost no data? This is where Katie Bouman entered the story. As a PhD student in computer science at MIT, Bouman had been developing an algorithm called CHIRP, Continuous High-Resolution Image Reconstruction using patch cores. Her approach was elegant. Instead of trying to fill in the missing data with guesswork, she trained the algorithm on thousands of possible images of what a black hole could look like, based on the physics of general relativity. The algorithm learned the patterns of light and shadow that were physically possible. Then, when fed the real data from M87, it searched for the reconstruction that best matched both the measurements and the laws of physics. But here was the terrifying catch. With sparse data, there could be many possible images that fit the measurements equally well. The team needed a way to know which one was real. They built a gauntlet. 4 independent imaging teams, each using different algorithms, received the same data in isolation. None of them knew what the others were seeing. If they all produced the same image, the team could be confident it was not a computational hallucination. For months, the teams worked in secrecy, refining their reconstructions, testing them against simulated data, and arguing over what was signal and what was noise. The pressure was immense. A single mistake, a misinterpretation of the data, a bug in the code, and the first direct image of a black hole would be a mirage. But when researchers looked closer, the data revealed something impossible. Everything they believed up to this point was wrong. The problem was not that the data was incomplete. The problem was that the data itself was a kind of lie. Each telescope in the array had recorded radio waves arriving from the vicinity of M87, but those waves had traveled 55 million years to reach Earth. Along the way, they had been scattered by interstellar plasma, distorted by the Earth's atmosphere, and corrupted by the electronics of the receivers themselves. What the team had on their hard drives was not a clean signal. It was a tangled mess of noise, buried beneath layers of interference, and they had to disentangle it without knowing what the true signal looked like. This is where the physics of interferometry becomes almost philosophical. When you combine signals from 2 telescopes separated by thousands of kilometers, you are not simply adding their data. You are measuring the phase difference between the 2 incoming waves, the tiny offset in their arrival times, and using that to reconstruct the structure of the source. But the phase measurement is exquisitely sensitive. A change in the atmosphere above one observatory, a gust of wind shaking a dish, even the thermal expansion of a cable in the afternoon sun can introduce errors that completely destroy the measurement. The team had to calibrate these errors for every single telescope, for every moment of the observation, across the entire 10-day campaign in April 2017. The calibration process was a nightmare of bookkeeping. For each baseline, each pair of telescopes, the team had to measure the system temperature, the gain of the receiver, the pointing accuracy of the dish, and the delay introduced by the atmosphere. They used water vapor radiometers to measure the amount of water in the air above each observatory, because water vapor delays radio waves in a frequency-dependent way. They monitored the position of known quasars, bright, distant radio sources, to track the stability of the array. They even accounted for the rotation of the Earth, which changes the baseline geometry from moment to moment. The data was so vast and so complex that the correlation process, running on a dedicated supercomputer at the Haystack Observatory, took several weeks just to align the raw signals. But when the correlation was complete, what emerged was not an image. It was a collection of visibility amplitudes and phases, mathematical quantities that describe the interference pattern between each pair of telescopes. These visibilities were scattered across a plane called the UV plane, which represents the spatial frequencies sampled by the array. The problem was that the 8 had only sampled a tiny fraction of the UV plane, like trying to reconstruct a photograph from a handful of random pixels. The gaps in the data were enormous, and here was the cruel irony. The most important feature of the image, the dark shadow of the black hole itself, was the hardest to reconstruct because it corresponds to the lowest spatial frequencies, which were the most poorly sampled by the array. The team had to invent a way to fill in those gaps without inventing a false image. They turned to a mathematical technique called regularized maximum likelihood imaging. The idea was simple. Among all possible images that fit the sparse data equally well, choose the one that is most consistent with our prior knowledge of what a black hole should look like. That prior knowledge came from Einstein's equations of general relativity, which predict the size and shape of the shadow with extraordinary precision. The algorithm, developed by Bouman and her collaborators, used a Bayesian framework to assign probabilities to different reconstructions, favoring those that were smooth, that had sharp edges only where physics demanded them, and that contained no structures smaller than the resolution of the array. But even with these constraints, the algorithm could produce thousands of plausible images. The team needed a way to test whether their reconstruction was real, and that is when they devised a method so ruthless it bordered on paranoia. The team built a simulation gauntlet. They injected synthetic black hole images, thousands of them, each with slightly different physical parameters, into the same pipeline their real data would travel through. They corrupted these fake images with realistic noise, scattered them across the same sparse UV plane coverage, and fed them to the reconstruction algorithms. Blind. If the algorithms could recover the original synthetic image from the corrupted sparse data, then the team could trust the method. If the algorithms produced hallucinations, images that looked plausible but were completely wrong, then the team would know their reconstruction was unreliable. The results were sobering. The algorithms performed well on bright, large-scale structures like the accretion disk, but they consistently struggled with the dark central shadow. The very feature the team was trying to image was the most vulnerable to being erased or distorted by the reconstruction process. The solution required a radical shift in strategy. Instead of treating the image reconstruction as a single monolithic problem, the team broke it into layers. They first reconstructed the large-scale structure of the accretion flow, using only the short baselines, pairs of telescopes close together on Earth, which capture the broad, diffuse emission. Then they used the long baselines, telescopes separated by thousands of kilometers, like the one between the South Pole Telescope in Antarctica and the James. Clerk-Maxwell telescope in Hawaii to add the sharp, fine-scale details of the shadow. This multi-scale approach allowed the algorithm to build the image hierarchically, starting with the reliable, well-sampled features and adding the fragile, poorly sampled shadow only after the large-scale structure was locked in. But even this was not enough. The team realized that any single reconstruction, no matter how carefully constrained, could be a statistical fluke. They needed an ensemble. They generated hundreds of independent reconstructions of the M87 data, each starting from a different random initial condition, each using slightly different regularization parameters. Then they averaged them together. The final image, released on April 10, 2019, was not a single photograph. It was a statistical composite, the average of thousands of possible images, each consistent with the data and the laws of physics. The bright, asymmetric ring was present in nearly every reconstruction. The dark, central shadow was present in nearly every reconstruction. The team could now assign a confidence level to every pixel in the image, and the shadow, the feature that would confirm Einstein's theory of general relativity at the very edge of a black hole, was there with a confidence that exceeded 5 sigma, the gold standard for discovery in physics. The announcement on April 10, 2019, was a global event. Simultaneous press conferences were held in Brussels, Santiago, Shanghai, Taipei, Tokyo, and Washington, D.C. The image appeared on the front page of every major newspaper. But for the scientists who had spent 2 years wrestling with the data, the most profound moment came later, in the quiet of their offices, when they compared their reconstructed image to the predictions of general relativity. The shadow's diameter was 42 microarcseconds, exactly what Einstein's equations predicted for a black hole of 6.5 billion solar masses. The ring's asymmetry, brighter on the southern side, matched the expected Doppler boosting from gas orbiting at near light speeds. The image was not just a picture, it was a measurement. And the measurement confirmed that general relativity holds in the most extreme gravitational environment in the known universe. But the image also raised a deeper question, one that the team is still grappling with today. The shadow of M87 is remarkably smooth. There are no substructures, no knots, no bright spots that would indicate turbulence or magnetic instabilities in the accretion flow. The gas around the black hole appears to be almost perfectly quiescent, flowing in a steady, laminar manner. This is not what the theoretical models predicted. Most simulations of accretion onto supermassive black holes produce chaotic, turbulent flows with complex magnetic field structures. The smoothness of M87's shadow suggests that either the gas is being held in place by an extremely ordered magnetic field, or that the black hole itself is spinning so rapidly that it is dragging space-time around it, smoothing out any irregularities. The data cannot yet distinguish between these possibilities, and that is the nature of science at the frontier. Every answer generates new questions. The first image of a black hole was not the end of a story. It was the opening frame of a much larger picture, one that we are only beginning to see. The smooth, perfect ring of M87's shadow had been extracted from 5 petabytes of noise, but the team knew they had only seen one side of the story. The image was a time exposure, averaged over the 10-day observing run in April 2017. It showed the black hole as a static object, frozen in a single moment. But black holes are not static. They spin, they feed, they erupt, and the Event Horizon Telescope had captured only a single snapshot of a dynamic, evolving system. The real prize, the thing that would unlock the physics of space-time itself, was not the image. It was the movie. The problem was that the H could not make a movie. The array's sparse coverage of the UV plane meant that any single frame contained barely enough information to reconstruct a static image. To capture variability, the flickering of the accretion flow as hot gas spiraled inward, the team would need to divide their data into time slices, each containing only a fraction of the already sparse measurements. The signal-to-noise ratio would plummet. The reconstruction algorithms, which struggled with a full 10 days of data, would fail entirely on a single hour. But the team had a trick. The black hole's shadow is not random. It is governed by the equations of general relativity, which predict exactly how the accretion flow should evolve over time. If you know the physics, you do not need to measure every frame. You can let Einstein fill in the gaps. This was the insight that led to a new approach, dynamical imaging. Instead of reconstructing each time slice independently, the team built a model of the accretion flow that evolved smoothly in time, constrained at every step by the laws of physics. The algorithm, developed by Michael Johnson and his collaborators at the Harvard-Smithsonian Center for Astrophysics, treated the black hole's environment as a fluid governed by magnetohydrodynamics, the same equations that describe the behavior of plasmas in fusion reactors and solar flares. The model predicted that the accretion disk should be turbulent, with hotspots and magnetic instabilities that cause the brightness of the ring to fluctuate on timescales of minutes to hours. The team fed their sparse, time-sliced data into this model and asked it to find the most likely evolution. The result was not a single movie. It was a family of possible movies, each consistent with the data and the physics. But when the team examined these dynamical reconstructions, they found something that challenged their fundamental understanding of black hole accretion. The variability was too slow. The hotspots in the accretion flow were moving at speeds that were significantly lower than the orbital velocity predicted by general relativity for material, so close to the event horizon. Either the gas was being braked by some unknown mechanism, perhaps a strong magnetic field threading the black hole, or the emission was coming from a region farther out, where the orbital speeds are lower. The team could not tell which explanation was correct because their data was still too sparse. They needed more telescopes. They needed more baselines. They needed to fill in the gaps in the UV plane that made their reconstructions ambiguous. The solution was already being built. In 2018, a year after the first observing campaign, the ET added 3 new observatories to the array: the Greenland Telescope, the Kitt Peak 12-meter telescope in Arizona, and the Noema Array in the French Alps. These new stations added critical long baselines, particularly the transatlantic link between Greenland and Europe, which would sample spatial frequencies that the original array had missed entirely. The team also upgraded their recording hardware, increasing the bandwidth from 4 GHz to 8 GHz, effectively doubling the amount of data they could collect in a single observing run. The next campaign, scheduled for 2020, promised to produce images with twice the resolution and 4 times the sensitivity of the 2017 data. But then the pandemic hit, shutting down observatories across the globe and delaying the next observation by 2 years. When the array finally resumed operations in 2022, the team faced a new challenge. The upgraded hardware and additional stations meant that the data volume had increased from 5 petabytes to nearly 20 petabytes. The correlation process, which had taken weeks in 2017, now required months. The imaging algorithms, which had been optimized for sparse data, needed to be completely rewritten to handle the new, denser UV plane coverage, and the team had to do all of this while also processing the data from the 2017 campaign for a second target, Sagittarius A, the supermassive black hole at the center of our own Milky Way galaxy. Sgr A is 1,000 times closer than M87, but it is also 1,000 times smaller, making its shadow roughly the same angular size on the sky. The challenge was not resolution. The challenge was variability. Sgr A's accretion flow changes on timescales of minutes, not days, because its event horizon is so much smaller. The team would need to reconstruct a movie of a black hole that was flickering faster than their telescopes could track. The first images of Sgr A, released in May 2022, confirmed that the shadow was there, exactly where Einstein's equations predicted. But the image was blurrier than M87's, smeared by the rapid variability of the accretion flow. The team had to average over entire nights of data to get a single static frame. The movie would have to wait, but the data from that campaign contained something the team had not expected: a flare. For a brief period, lasting about 40 minutes, the brightness of Sgr A increased by a factor of 10. The team had captured a snapshot of the black hole in the act of feeding, a blob of hot gas falling across the event horizon and releasing a burst of energy as it crossed the point of no return. The image of that flare, reconstructed from just a few minutes of data, showed a bright knot of the mission moving along the edge of the shadow at relativistic speeds. It was the first direct observation of plasma orbiting at the edge of a black hole, and that is when the real scientific puzzle emerged, one that still has no answer. The flare's trajectory did not match the predictions of standard accretion models. The hotspot appeared to be moving in a retrograde orbit, opposite to the direction of the black hole's spin. Either the accretion flow was counter-rotating, which would require a dramatic reversal of angular momentum, or the black hole itself was spinning in the opposite direction of the gas falling into it. Both possibilities are allowed by general relativity, but neither was expected. The team is still analyzing the data, running simulations to test whether a counter-rotating accretion flow can remain stable for long enough to produce the observed flare. The answer will tell us something fundamental about how black holes grow and evolve over cosmic time. It will tell us whether the supermassive black hole at the center of our galaxy is a gentle giant, quietly sipping gas from a well-ordered disk, or a violent predator, tearing apart anything that falls within its gravitational reach. The image was just the beginning. The movie is the truth, and we are only now learning how to watch. The ring of M87's shadow was not the final answer. It was a single frame in what the Event Horizon Telescope team knew had to become a motion picture. But to capture the dynamics of space-time itself, the swirling, chaotic dance of gas as it spirals into oblivion, they needed to see how that ring changed, and that required tearing apart their own masterpiece. The team took the 2017 data and sliced it into time windows. Each slice was a fraction of the total observation, containing only a whisper of the already sparse signal. The reconstruction algorithms, which had barely managed to produce a static image from 10 days of data, were now asked to produce a coherent picture from a single hour. The noise was overwhelming. The gaps in the UV plane were cavernous. And yet, when the team applied their dynamical imaging techniques, forcing the reconstruction to evolve smoothly in time, constrained by the magnetohydrodynamic equations that govern accreting plasma, something remarkable emerged. The ring was not static. It was shimmering. The shimmer was subtle, barely above the noise floor, but it was there. The brightness of the ring fluctuated on time scales of hours, with hotspots appearing and disappearing along the edge of the shadow. These hotspots were not random. They were moving, and their motion told a story. The gas in the accretion disk was orbiting the black hole at relativistic speeds, completing a full circuit in just a few days. But the hotspots were not moving at the same speed as the underlying gas. They were moving faster. This was a signature of a phenomenon predicted by general relativity but never before observed: orbital motion in the strong field regime, where spacetime itself is being dragged along by the black hole's rotation. The effect is called frame dragging, or the lens-thurring effect. It occurs when a rotating black hole twists the fabric of space-time around it, dragging nearby objects along with its rotation. For a particle orbiting close to the event horizon, the effect is dramatic. The particle's orbital plane precesses. It wobbles like a spinning top, and the precession rate depends on the black hole's spin. The hotspots in M87's accretion disk were precessing at a rate that implied the black hole was spinning at nearly the maximum possible speed, close to the theoretical limit, where the event horizon itself would begin to break apart. This was a measurement that no other technique could have made. It was a direct probe of the geometry of space-time in the most extreme environment in the universe, but the measurement came with a cost. The dynamical reconstruction required the team to make assumptions about the structure of the accretion flow, assumptions that might not hold in reality. The magnetohydrodynamic simulations that constrained the reconstruction were based on idealized conditions, a steady axisymmetric inflow of gas with magnetic fields that were initially weak and turbulent. But M87 is not an isolated black hole. It is the engine of a relativistic jet that extends thousands of light-years into intergalactic space, powered by the extraction of rotational energy from the black hole itself. The jet is launched from the inner accretion flow, where magnetic fields are amplified to enormous strengths, threading the event horizon and channeling plasma into a narrow, collimated beam. These magnetic fields could alter the dynamics of the hotspots, suppressing turbulence and changing the precession rate. The team could not distinguish between the effects of black hole spin and the effects of magnetic fields with their current data. The resolution of this ambiguity would require a new technique, polarimetry. Radio waves emitted by hot gas near a black hole are not randomly oriented. They are polarized, meaning their electric fields vibrate in a preferred direction. The polarization angle is rotated by magnetic fields along the line of sight, an effect called Faraday rotation, and the degree of polarization reveals the orderliness of the magnetic field structure. By measuring the polarization of the radio waves from M87, the team could map the magnetic field lines around the black hole, determining whether they were ordered and strong enough to launch the jet, or chaotic and weak. The 8 had been collecting polarization data since its first observations in 2017, but the calibration was extraordinarily difficult. Polarization measurements require precise knowledge of the orientation of each telescope's receiver, the phase stability of the entire array, and the atmospheric conditions above every observatory. A single degree of error in the polarization angle could produce a false magnetic field map. The team spent 2 years calibrating the polarization data. They used observations of known polarized sources, calibrators like 3C279, a bright quasar, to measure the instrumental polarization of each telescope. They developed new algorithms to correct for Faraday rotation in the Earth's ionosphere, which changes with the solar cycle and the time of day. They even accounted for the polarization introduced by the reflective surfaces of the telescope dishes themselves, which can rotate the polarization angle in a frequency-dependent way. When the calibration was finally complete, the team produced the first polarized image of a black hole's accretion flow. The image, released in March 2021, showed a pattern of magnetic field lines wrapped around the shadow in a tight spiral, consistent with the presence of a strong, ordered magnetic field threading the event horizon. The field was strong enough to launch the jet, and the polarization pattern confirmed that the black hole was spinning rapidly, because only a rapidly rotating black hole can produce the observed twist in the magnetic field lines. But the polarized image also revealed a mystery. The magnetic field was not uniform. It was organized into a series of concentric rings, each with a different polarization angle, suggesting that the accretion flow was stratified into layers with different magnetic properties. The inner ring, closest to the shadow, had a polarization angle that was nearly radial, pointing directly toward the black hole. The outer ring had a polarization angle that was azimuthal, wrapping around the shadow. This transition from radial to azimuthal polarization is a signature of a physical process called magnetic reconnection, where oppositely directed magnetic field lines snap and release energy. The reconnection was happening at a specific radius, about 5 times the size of the event horizon, and it was heating the gas to temperatures of billions of degrees. This was the first direct evidence that magnetic reconnection is the mechanism that powers the X-ray emission from black hole accretion flows, a process that had been theorized for decades but never observed. The implications were profound. Magnetic reconnection is the same process that drives solar flares on the sun, but around a black hole, the energy release is billions of times more powerful. The reconnection events in M87's accretion flow are producing high-energy particles that are then accelerated along the magnetic field lines into the jet, powering the enormous structures seen by radio telescopes across the globe. The black hole is not just a passive gravitational object. It is an engine, converting the rotational energy of space-time into electromagnetic radiation and relativistic particles, shaping the evolution of its host. Galaxy over cosmic time. The image of the shadow was a portrait. The polarized image was an autopsy. It revealed the inner workings of the engine, the magnetic machinery that drives the most powerful phenomena in the universe. And yet, for all that the polarized image revealed, it also raised a deeper question, one that cuts to the heart of our understanding of gravity itself. The magnetic field structure around M87 is remarkably ordered. It is not the chaotic, tangled mess that most simulations predict. The field is coherent over scales of tens of billions of kilometers, wrapped around the black hole in a tight, organized spiral. This order suggests that the accretion flow is not turbulent, but laminar, a smooth, steady inflow of gas that has been flowing for millions of years. But laminar accretion flows are unstable. They should break apart into turbulence within a few orbital periods, unless something is holding them together. That something might be the black hole's spin, which drags space-time around it and suppresses turbulence by shearing the gas into ordered layers. Or it might be something far stranger, a fundamental modification of general relativity itself, in which the equations that govern gravity are different in the strong field regime. The team is now testing this hypothesis. They are running simulations of accretion flows in modified theories of gravity, such as scalar tensor theories and Einstein dilaton-Gauss bonnet gravity, which predict deviations from general relativity near the event horizon. These deviations would change the size and shape of the shadow, the precession rate of the hotspots, and the polarization pattern of the emitted radiation. The 2007 data is not precise enough to distinguish between general relativity and these alternative theories. But the 2017-2 data, with its doubled resolution and quadrupled sensitivity, might be. The team is currently analyzing that data, comparing the observed shadow and polarization patterns to thousands of simulated images generated from different theories of gravity. The answer will come within the next year, and when it does, we will know whether Einstein's theory holds at the very edge of a black hole, or whether we have finally found the crack in the foundation of modern physics, the first experimental evidence that our understanding of gravity is incomplete. The universe is not only stranger than we suppose, it is stranger than we can suppose.